So today we are going back to the basics and we are getting to know Lambda. We're getting to know failure rates, getting to know fits, and everything about them. So as I said, we are doing another of these back to basic webinars today. And if you've been keeping up with the blogs that we've been posting, the latest handful were about different types of failure rates, what a failure rate was. So I wanted to take this time and recap the last few blogs that have been posted and even a couple sneak peek on the next few that are coming up. Take a deeper dive into it in this webinar format and answer any questions that you might have. So today like I said before, we're really focusing on failure rates in Lambda. We're going to get to know what failure rates are, how to find one, what to do, all the different kinds, and why they really matter. My name is Loren Stewart, and I'm a CFSE here at exida. I've been working with exida for over 8 years now, working with most of our mechanical customers, helping them achieve IEC 61508 certification. Or I also work a lot with our exida Academy branch. I do trainings, courses, teachings, and these webinars and such. For those of you that aren't familiar with exida yet, welcome. I do see a few new names that I haven't seen before. So just in case you're not familiar with exida, we are involved in the complete supply chain of functional safety in multiple different industry sectors. Anywhere from the people making the equipment going into safety systems who need product certification, tools, FMEDAs, consulting, the whole way through to the end users who use those products in safety systems. exida provides software, tools, training, consulting, certification, personnel certification, templates, procedures, all related to functional safety, security, and reliability. I like to say no matter where you are, where your products are coming from, where your products are going, where your customers are, we have people close by, experts in the fields of functional safety, alarm management, and cybersecurity that can help you along with any of the projects you need. And last slide about exida, and then we'll dive into why you're really here today. But I always make sure my customers know to keep checking back to all of our resources. This is definitely a key place where we try and communicate all of the latest and greatest, the most up-to-date research, all of our knowledge. We do this in all sorts of different forms of media through these free webinars, the blogs that I was speaking of earlier, white papers that you can download for free on our website. We go to conferences, we give speeches, we do trainings and teaching and courses. We try and get whatever we're researching, the latest and greatest information out there, because it's not doing us any good keeping it close. We want to try and make the world a safer place. So always check back to see what we're publishing, what we're getting out there if you want the latest and greatest information. So let's get into why you're here today. All about failure rates. We're going to talk all about them in this webinar, starting from the very, very basics. And if you have any questions throughout this webinar, please let me know. I'm not very good at stopping throughout the webinar and pausing and taking time for questions. I kind of just get on a roll and just keep talking away. But at the end, I'll make sure to take some time and answer any questions. We can flip back in the slides if we need to. And you can just put any questions you have in the little panel of your GoToWebinar, and I'll pick those up later. So as I said, we're going to start at the very, very beginning and just define what a failure rate is. So we're all using the same vocabulary, the same terms, and all on the same page. Then we're going to look at what the standards say, what they define, what they say you can do with them, what you need to do with them, everything from their unit of measurements, the different types of failure rates, different types of failure modes, where can you find failure rates, how do you get them, how does a product obtain failure rates, how do you know if a failure rate you have for a product is good for your application or not, and if it's not, what do you do then? And then finally, we're going to look at why failure rates are important and sum it up, kind of why they matter. So as I said, there's a ton to cover today, so let's just dive right in. So what is a failure rate? Well, failure rates are the number of failures per unit time for a piece of equipment. It's usually assumed to be a constant value and can be broken down into several different categories. There can be safe failures, there can be dangerous failures, there can be detected and undetected failures, there can be independent or normal or even common cause failures. Failure rates are often expressed in this term, the lambda, the big red Greek symbol in the middle of your screen. And it's usually called a unit of measurement called a fit. And we will get into those lambdas and those fits all later in this webinar. So what do the standards say about failure rates? Well, both IEC 61508 and IEC 61511 define failure rates. They use them in assessments and they use them in equations. In the old versions, in the first versions of the standards, they used to just say, oh yeah, this is what a failure rate is, and you need to use them in your calculations. But both IEC 61508 and IEC 61511, when they did their newest revisions of the standards, they took it further. They, instead of just saying, well, this is what failure rates are, they say not only this is what they are, you need to use them in assessments, you need to use them in equations, and not only that, they need to be credible, traceable, documented, and justified. So what does that really mean? That means that it needs to be appropriate for your application, your demand, your operation, your environment. It needs to come from a place that has been documented, and it needs to be credible information. And this language, like I said, it kind of definitely got kicked up a notch in the newest versions. And that strong language just reinforces what us reliability engineers have always understood. We know that no matter how good your calculations are or how great your software might be, if you put failure rates that are not credible or not justified for your application into these software or equations, what comes out is going to be worthless. So this language has gotten stronger in the new standard, and hopefully it's going to lead to the end of unrealistic failure rates and those being used in calculations. So how are failure rates measured? Well, you might have heard of things before called a fit. Well, that's usually what we're dealing with when we talk about failure rates. A fit could be described, I've heard both ways, and both ways are correct, failures in time or failure units. But they both mean the exact same thing. It is the number of failures per billion hours for a piece of individual equipment. It is mentioned, as I said, both in IEC 61508 and IEC 61511, and its preferred unit of measurement is usually 10 to the negative 9 hours. That's per billion hours. So when you hear people talk about failure rates they get from a certificate or from an FMEDA, a failure mode effect and diagnostic analysis report, they are generally speaking in terms of fits. So you might hear something like, oh, it is 5 fits for that screw, or this valve is 500 fits. Well, that 5 fits and 500 fits, that technically means 5 to the 10 to the negative 9, or 500 times 10 to the negative 9. And that's how it's described. These failure rates can be broken up into safe, detected, undetected, dangerous, detected, undetected, and we will get into all the different types and exactly what they mean in different applications later on. But these failure rates are extremely important pieces of information for the end users. These failure rates go into very significant end user equations such as your PFD average or PFH calculations and other SIL verification tasks. So it's absolutely imperative that they are not only right for your application, your operation, your demand, and your environment, but they're also realistic and correct. So what are the different types of failure rates and failure modes that you might have heard of or might have come across? Well, as we started off, we know a failure rate is a lambda, and that lambda is a Greek symbol at the top, and it can be expressed as the total failure rate for a device, meaning anything from as simple as a little switch to a complex type B device, complex device with internal diagnostics and software, and anything in between. That lambda total, or I've seen it as lambda T as well, can be broken down into more specific grouping of failures. If a failure is going to take the situation into a safe state, or if that will be taken into a dangerous condition if that failure happens. When we talk about these failure rates, we will later we'll get into what exactly they mean and even examples of safe and dangerous failures. But the easiest way to know a device's failure rates or a device's lambda is from the FMEDA, or failure mode effects and diagnostic analysis report, or a back of the certificate. As I said, that lambda total can be broken into safe and dangerous failures. That lambda S representing that safe failure or your spurious trip rate. And once again, in functional safety, those are going to be given in unit of measurement of fits. The lambda D is going to be the number of dangerous failures per unit time for that piece of equipment. And it's going to be the time where a failure would actually prevent the safety instrumented function to perform its intended job. So your SIF cannot achieve a safe state. Both these safe failures and these dangerous failures can then be broken up into further subcategories, whether they're detectable or whether they're undetectable by the device's internal diagnostics. So for example, we have the lambda D can be further broken up into lambda DD and lambda DU. The DD being your dangerous detected failures, and your DU is your dangerous undetected failures. And that is detected by those internal diagnostics. Let's take a deeper dive into what both of those mean. So as I said before, that lambda S is your safe failures, your spurious trip rate. It's going to be any failure that does not have the potential to put your safety instrumented system in a dangerous or fail to function state. So that seems good, right? It is a situation where your safety-related system or a component fails to perform properly in such a way that it calls for the system to be shut down when there's no hazard present. So what does that really mean? In process industries, you can usually hear of this as a spurious trip. This means that you're operating in normal conditions. Everything's running smoothly, it's going well. For some reason, a failure occurs and your device thinks that a hazard has come up and it needs to shut down. But you're in normal operation, everything's going fine, and it shuts down unnecessarily. So even when nothing is wrong, your process is running normal, you're great, you're smooth, your emergency shutdown system kicks in and takes you to that safe state. And that's not good. So the lambda SD would be those safe detected failures. What does that mean? That would be, once again, you're in normal operation. It takes you to a safe state when not necessary. So the safe detected failure would be when your internal diagnostics can let you know before taking you to that safe shutdown occurs. The safe undetected failures are those undetectable spurious trip rate. Once again, it's going to be in those fits, just like the safe failures, safe detected failures. And it's going to be when everything's running smoothly, there does not need to be a shutdown, and your diagnostic did not catch this in time, and this device took you to that safe state when it was not necessary. Did not need to be done, but you're still shut down. So if you think about it, those safe undetected failures are a much bigger deal than those safe detected failures. At least if you're detecting it from internal diagnostics, you have the opportunity to make the correction possibly before a shutdown would occur. So what are some examples of some safe failures? And depending on your internal diagnostics, these could either be safe or these are detected or undetected. So what if you have a loss of air pressure in an actuator? It causes your valve to close on trip and shuts down the application. Or what if you have an output fail open and it immediately goes to the safe state? Both of those, your process would be running normal in normal operating conditions, and depending on your internal diagnostics, if it caught it in time or not, you could be in a shutdown situation unnecessarily. So knowing your safe failure rates can really help you prevent unwanted and unneeded process shutdowns. And we all know those. We don't want those process shutdowns. We don't want you to have those process shutdowns. Those can not only be frustrating, but those can also be very costly. So I know that the dangerous failure rates are famous. They are those big scary ones that everybody talk about. They're in the equations. They're the ones that get all the spotlight and all the attention. But don't forget that the safe failures are important too. So even if it's tempting to only consider the dangerous, it's really take a moment and think about your safe failure rates, your possible spurious trip rate. And if you could move some of those, maybe add diagnostics, some of those undetected shutdown spurious trips to detected, or even lower your spurious trip rate altogether, that would be less frustrations, maybe less shutdowns, less time down, save you some money, hopefully. On the other hand, we have the famous lambda Ds. Those are the dangerous failures, the dangerous failure rates. It's going to be exactly what we don't want. It is a time where a failure would prevent a safety system from performing its intended job. And the SIF cannot achieve a safe state if needed. Just like the safe failures, they can be broken down into dangerous detected or dangerous undetected. Both the dangerous detected and dangerous undetected are going to be given to you in fits, that 10 to the negative 9 failure rate. They can be found on back of certificates or FMEDA reports. The DD, the dangerous detected number, that of course will depend on your internal diagnostics. How much of those undetected failures are you searching for? How many can you find? And what would happen if that really happened? What does a dangerous detected failure mean? Well, a dangerous failure would be a time where the safety system can't do its job. It can't achieve a safe state. So if you have a dangerous detected failure, it would be when that failure would prevent it from doing its job. However, because of your internal diagnostics, you were alerted to this could be happening. You were given an alarm, you were given a warning that something is not right here. And until the SIF is fixed, you cannot achieve a safe state. So you understand that you might be able to continue, but you are in a degraded condition. Your operators need to be aware that if something happened, you cannot rely on your safety system. But once again, if you have detected those failures and you have those DDs, those will give you the opportunity to act or to fix it before you completely are in trouble and have no safety system. So having dangerous detected failures are much better than those scary, scary DUs. Those DUs, those dangerous undetected failures. Those are the ones we hear about. Those are the ones that we stay up at night worrying about. Those are the failures that we don't know are lying, waiting in the shadows for us to just pounce our safety systems when need be. What does that really mean? Well, the dangerous is where you can't do its job. Your SIF can't jump into action if needed. So a dangerous undetected would be some type of failure that prevents the safety system from doing its job when it needs to, and it was unnoticed by any diagnostics. So if the SIF needs to jump into the action, it can't. It cannot achieve safe state if needed. So what are some examples of some dangerous failures? Once again, depending on your diagnostics, these could be dangerous detected or dangerous undetected. So for example, you could have a ball valve, and if the valve stem is sheared from the ball, you could think you are moving the actuator, and you think you're moving the ball, but in reality, the ball isn't moving and cannot shut the valve in time. Or you have a solenoid signal and it's not alerting the actuator that something needs to change. What if you have a pressure sensor that is not working and it's high pressure, supposed to shut down the system? It goes over that pressure, you don't know about it. You could have a valve getting stuck in an open on-trip application. It hasn't been used in too long, corroded shut. It needs to close, can't. What about a transmitter shorting? So all of these could be dangerous detected or undetected depending on your diagnostics. And as I said, these failures are the super important ones. These are the ones to keep your eye on. These are the ones to really know about. They're going to be on the back of the certificates, in the FMEDA reports. They are the ones that are going directly into the SIL calculations that end users do. That's why they're so important. So not only knowing this number, but making sure it's credible, justified, traceable, realistic is absolutely key. So there are other types of failure rates as well. They're not as popular as the safe or the dangerous. And kind of for a reason. They're not necessarily as important either. But they are good pieces of information to know. They don't necessarily directly impact your safety system's ability to do their job. But it's good information. Things like lambda A, lambda NE, or lambda E. These are things like your enunciated failures, your lambda A's, your your external leaked failures, your lambda E's, and your no effect failures, or your lambda NE's, or your residual failures. The enunciated failure is a failure that really has no effect on the safety function, but it does affect the ability to detect failures and future faults, and for an individual unit and piece of equipment. What does that mean? This usually just deals with your internal diagnostics. So this failure will still let the safety system work. It will still close that valve if the valve needs to close. It will still detect a failure. However, you might not know if there's normally detected failures arise. Those detected failures, those DDs, now might come DUs, or those SDs might become SUs because you don't know about them. Some examples of an enunciated failures could be maybe you have an internal diagnostic circuit of equipment, or your display might not be showing. So you have an issue with your internal diagnostics. They're trying to alert you that something's going on and you just don't see it's coming. Another other failure rate is your no effect or your residual failures. These no effect failures once again are going to be given through the FMEDAs. They're usually not on the certificates because they're not as important. But they're the number of failures that really don't affect the safety system at all. A residual or a no effect failure, which would occur in normal operation, and it just lets the safety system continue working as it should. The process can still be taken to the safe state if needed. But it is good to be aware of these no effect failures, especially if you have a very dangerous or hazardous process. Some no effect failures could be external leaks or small internal leaks, display issues, a bolt loosening, or maybe one of 12 bolts breaking off. So they're good to be aware of, but it's not something that will prevent the valve from closing at the end of the day. There's a special type of no effect failure that's subcategory, and that is the external leaks. This is broken out individually just in case you have a very hazardous or a very toxic process going through. You want to be aware if it's possibly leaking and could harm your employees or the people around you, your equipment, or the environment. So if you have clean water going through your pipes, that might not be an issue. However, if it's something that could cause damage to those surrounding you, once again, that external leak might be something great to know. As I said, most of the time these failures don't show up on the certificate. There's just not enough room to put all of these pieces of information. But if you look at the FMEDA report, they will always break it out for you if it is relevant. So where do failure rates come from? There are two main ways of getting failure rates. There are failure rate estimation and failure rate prediction. So failure rate estimation is going to be based on failure reports using statistical techniques and tools to collect all of the data. The statistical analysis needs to have a good understanding of all of the equipment in operation, the common failure modes, the key environmental variables, how the equipment is used, how the data was designed by the designers, and to make sure it's in the same type of application. Once again, you don't want to be throwing subsea and cabinet mounted valves together in the same type of apples to apples comparison. So just taking a tally of field return data is definitely not enough to be for the estimation technique. You need to have sophisticated tools, software, and statistical analysis. The other way of getting failure rates is the predictive techniques. And this is designed on stress strength analysis. Both of these techniques have pros and cons on the way you do them, how they're done. We're going to and there are webinars that get into just this subject, but I'm just going to get into how we do the failure rate data at exida. We get into the predictive analysis from an FMEDA, a failure mode effect and diagnostic analysis. And this is that detailed analysis of every single component of any given design. So we look at the exploded view or some sort of cutaway view where you can really see how the product works in a detailed bill of material. And we go through every line of that bill of material and see how different stress that device will be seeing, how it handles that. Looking at the application, the environment, how it's going to be used, and seeing if it fails, if that could be a safe failure or a dangerous failure. The FMEDA technique is based off of the FMEA technique, but added in the components of diagnostics to be available. At the end of the FMEDA, you are presented with a product failure rate in that safe detected, safe undetected, dangerous undetected, a product failure mode, diagnostic coverage, and even useful life for the device. So the FMEDA analysis is both application specific, environmental specific, and it considers how the device works, how it's set up, where it will be operating. So it's very specific to how the stresses will be applied. And that's how you can get those specific failure rates for the applications. You will have a different failure rate, maybe for close on trip, then tight shut off, then open on trip. Different failure rates for subsea versus offshore versus cabinet mounted. Different failure rates for clean service, severe service, dynamic or static application, along with all of the different environmental profiles. Once you get the failure rates, they will be, as I said, listed in the product failure FMEDA report and on the back of the certificates. So how do you get a product failure rate? Well, you can ask for their certificate, or if you need to look up certificates, I always tell my customers to go to the SAEL. It's a great tool. You can say, I need ball valves that are certified for SIL 2 or SIL 3 application, and see a big long list of them. And you can pull up their individual certs from there. As you can see on the front of the cert, it'll give you a lot of great information. It'll tell you all about the device that's certified, the safety function, the application, how it was looked at systematically, and then on the back, all of your failure rates. It's going to be per application, per environment, and broken up into your safe, your dangerous, detected, and undetected. What happens if you don't have a certificate or you don't find a certificate. Then go back and ask for a FMEDA report or the failure rates. They should, whoever you're buying your products for should be able to give this, especially if it's a certified product, they will have this. If you're just given a FMEDA report or failure rates, even if you're just given a certificate, I always say, take the moment and you make sure it's right for your application, right for your environment, and ask how those failure rates were achieved. Is it the type of same apples to apples comparison? Or are you going to use a static test to give you results in a dynamic application? So make sure you are taking the failure rates appropriate for your exact conditions. So how do you know if the failure rates are appropriate for you in your application? Well, first of all, make sure it's right for your own device. So if you need the static or dynamic, if you need a subsea, the different types of environments, the different types of operation, clean versus severe. So make sure all of that has been identified. Then you can get the failure rates that you receive from the FMEDA reports or from the certificates. And here's where this is my reality check. SILSafeData.com. So this will let you know if you are kind of in bounds and what to expect to see for failure rates. So I know you can't really see this, so let me zoom in real quick. So for example, we look at an actuator. Let's look at a spring return actuator. Let's say you were trying to buy this actuator and someone said, well, here's my field return data, and it says my failure rate is 17 fits. So you come to SIL Safe Data and say, 17 fits. Does that make sense to me? And this is your dangerous undetected failure rate here, your DUs, because that's the important one that goes in all of your SIL calculations, and say, okay, so a normal spring return actuator, we should see anywhere from 400 to 1250 fits. That's a little, maybe if it was like 380 or 1300, we could understand, but a whole order of magnitude off, that seems to raise red flags. So if you ever question if your failure rates are too good to be true or pass the smell check, or you want a reality check, come to silsafedata.com and look up. We have a bunch of devices. We don't have everything. We are continually adding more. So if you see things that you need that aren't there, let us know. So we did a comparison of solenoids, and we looked at all sorts of different things, from the exida database, which is an offshore reliability handbook that deals with subsea and offshore real life data and failures from the North Sea, which is an amazing database. We have pipeline company databases. We have the Dow field database. We have the Siemens database, the old mill handbook database. So we compared solenoid failure rates from FMEDA's, all of these different databases, and plot those along with some of those too good to be trues. And we also looked at that SIL Safe Data line, and depending on what the complexity of your solenoid, we know there's different, the spool is going to be more complex than a little poppet. You can see that some of these did not pass that reality check. When we looked back, we asked questions why. There could be things like they were using a static test and extrapolating the results for a dynamic application, which wasn't valid, or only looking at their returns and saying, oh, that's our failure rate. So that's why I always say, when you receive them, always ask where this information came from, and also do your reality check. Because if these are numbers, well, if you're using it in marketing, whatever, that it's not necessarily good, but if these are numbers going into calculations, you have to make sure they're right. So what do you do if it's not? What happens if you evaluate your failure rates and you look and say, oh, this isn't good? What do I do now? My failure rates are too good to be true. I don't feel safe and comfortable using them in equations. I wouldn't want my family next to something that was calculated with this. What do I do? Well, you're kind of in a tough situation, but there is a little way to help you out. You can always use generic numbers for your failure rates of your SIL verification calculations. I know it's not going to be great. It's going to be super conservative, but if that's all you have, it might be better than using unrealistic. They will be higher than just certified devices. They will, generic numbers just will be. But without knowing specifically more information or having better data, you can always go back to silsafedata.com and use this high bounds as a generic. Once again, as I said, it's going to be higher than probably most of those failure rates you would see on a back of certificate. However, if you have a lack of data, it could help you. With that said, if you're using a generic number, remember you're not going to be systematically capable qualified as you would be with a certificate. So where does the SIL Safe data get its information from? Well, all over the place. It has, it was a huge database compiled together with, this was a couple years ago, 200 billion unit operating hours of field failure data, plus all of the FMEDAs that we've ever done put in there, plus the ERIDA handbook, a chem handbook, and power handbook, the EMCRH component database, the military handbook, that I forget the MIL standard on that, the Siemens original database. All of those have been mushed together in this database to create that upper and lower bounds. And yes, some of those bounds may be large depending on the range of complexity available for those devices or pieces of equipment, but it could give you a starting point to help you get there. Remember, I've liked optimistic failure rates just can lead to bad and unsafe designs. I like to think of the standards as almost a bridge to safety. And if you do all the requirements and you document it correctly, you're going to get across safely. But if you start picking and choosing what parts of the standards you want to apply and what parts that you just don't feel like complying to, your bridge starts to weaken. The standard, remember at the very beginning, the standard says you have to be credible, traceable, documented, justified. Your failure rates need to be apples to apples. They need to be right for your application. So optimistic failure rates can simply lead to unsafe designs. This can happen by having way over optimistic failure rates. There might not be enough redundancy. Maybe you needed to have redundancy in your situation and your calculations said you didn't. Or it might provide insufficient testing. It might say you only need to test once every 10 years when that's not the case. So using wrong failure rates and overly optimistic can actually hurt your PFD average. It can hurt your risk reduction, and your SIL might not even be valid. What all you're doing is you're being an ostrich. You're pretending everything's great, just putting your head in the sand, just not wanting to know when you're going to explode. So to wrap it up, in the end of the day, I know failure rates are 10 to the -9. They're super, super, super tiny numbers. So it's hard to remember what's the big deal if it's 5 or 500. It's 10 to the -9. Come on. But the end of the day, these safety systems were put in place because the calculations determined opening your doors as is wasn't safe enough. These safety systems are to prevent serious and possibly deadly disasters. And at the end of the day, these calculations are all about making sure you are reducing enough personnel, environmental, and financial risk. So I was bad and didn't stop for questions throughout the webinar. I apologize, but let me take a moment now and open these up. In the meantime, if you have questions later that you think of and you want more information, please feel free to email me and visit our website. And that's also a place, as I said earlier, great place for references. Look at the books, the white papers, the webinars, the blogs. And then if you loved this so much and you need to have more functional safety in your life, because you know we all do, we have online and self-paced training. Even with all of COVID and travel bans and everything going on, you can still get yourself trained in functional safety. So check out our training and our online offerings. Okay, we have a question. How do you resolve the issue of low failure rates from assessment or FMEDA? They received a certificate of a user and it's low. Okay, they received a certificate, but even though it's a certificate, it still has data that's lower than the SIL Safe Data. Well, the first thing I would do is, well, there might be a reason, and there might be a good reason why. Maybe if you are in a dynamic application and you're moving all of the time, that could be one of the reasons. See how the analysis was done. Was it done by a FMEDA? Was it done by testing? Was it done by field failure? And just start asking why. If you don't feel comfortable using that information, if it's not apples to apples and you don't like it, then use that generic, that higher number on SIL Safe Data. Or you can also always have the FMEDA redone. Not necessarily go through the whole certification thing, but maybe just get the FMEDA and realistic failure rates. So you do have some options. They're not necessarily the easiest or best, because it would be much better if you could just get a certificate with what you liked on it, but you do have some options, and hopefully we can help you. And if not, just at least using that reality check or that SIL Safe Data can help you just know when to accept it or when not to. For equipment manufacturers, we are building the device from discrete components. How do you get the failure rates? These components normally do not have certifications. Well, if it is something like a medical device, you can always send that in to us and we can do the analysis for you. We can break it down per components as long as we have detailed on what all of those components are. We have the component database that has the history. We've been collecting it for 20 years that can help you with that. Especially medical wasn't necessarily first to adapt these, so I can definitely see where there was a lag getting this information to you. But the process industry has been there, and we have been collecting data, so we can help you with this. And yes, many don't have certifications, but that's yet. Things are moving in that direction, and you should be seeing a turn in that soon. That's all the questions that I have for this afternoon. Thank you so much for joining us. Please check back for more webinars, more blogs, and yeah, thank you. Let us know if you want more.